So this is 127, and today we're going to talk about format string vulnerabilities first, and then I'm planning to demonstrate the keep the waves coming. Well, I don't know what that is. Oh, the waves of Omicron, so you can stay remote. Well, yes. Well, I think there's no chance the college would go face-to-face anyway, but it may affect what other jobs you have. Anyway, so we're going to talk first about format string bugs, and then I'll demonstrate a buffer overflow project. But it might be a little rougher than usual because I was trying to update my stuff to Debian 11 and Python 3. Debian 11 is not much of a problem, but Python 3 turned out to be incredibly difficult. That's why I stuck with Python 2 for so long. Python 3 makes it very difficult to print out the strings containing raw, non-printable bytes, which are what you need for this kind of attack. So I finally just went back to Python 2 on Debian 11, and that's what I'm going to use to demonstrate stuff for tonight. And I'm probably going to leave the projects like that. Doing it in Python 3 is just too annoying. I may just put that off for another semester or year before I try to figure out how to print these raw hexadecimal strings in Python 3, which very much resists it. We're abusing strings. We're printing things that are not strings as strings, which you can do in C and in Python 2, but Python 3 really tries to stop you from doing that. So anyway, let's talk about format strings. And I am recording good. All right, so the fundamental problem with all this stuff we're doing, I had a lot of trouble. Anyway, I don't think I'll go into the Python 3 problems now. It'd be good if you can show me eventually how you did it in Python 3. I got the first couple of scripts running in Python 3, and then I couldn't get the next one running and just got fed up with it. They explained with woo ftpd could not install. Oh, yeah. I wouldn't worry about. Anyway, we'll do it with my vulnerability. Yeah, I think the book probably uses some old program that you can't run anymore. I made a simpler version. So, all right, the fundamental problem with everything we're doing here is that data is stored as raw bytes, and your computer does not know what those bytes are. It doesn't know if it's an image or a program or text. So here, that's the fundamental problem. So if you have data printed, let me just bring up my live demonstration here. All right. So here's my Debian machine, and let's see if I can get out of wherever I am. Yeah, okay. And clear. All right. All right, so I made a couple of simpler versions of this than what I originally had on the slide. Let's make this bigger. Okay, so cat format, cat I say. All right, so here I have an integer. I set it to 1001, and then I print it with a %d format string, which means decimal. So if you run that, it prints in decimal. That's what a %d means. So that's fine. And see, this binary data storage, it doesn't know what it is. It could be a character, could be, you could print it in hex, you could print it in decimal. So you have to tell it how you want to see it. Now, if we look at format 2, here I do the same thing. I print I with format D, but here I have this very strange command to print 3 values in hexadecimal, and there is no data there. So before I go there, let's look at this one in assembly. So this is format 1, where I'm just going to print that value. If I gdb -q my format 1, all right, and now I disassemble main. Okay, let's see if I can fit this junk on the screen. All right, so here's the printf function. Now remember how calls work. You push a value onto the stack, then you push another value on the stack, then you call it. So to see what's on the stack, let's put a breakpoint here at main plus 50, which is break star main plus 50, and run to that point. And now we can look at these values on the stack. We are here in this command. So the first value on the stack is at this location, EBP minus C. So we can examine, say, 4 hexadecimal values at EBP minus 0xC. All right. And so you see this word has 3E9, and these have other values. Now I examined them in hexadecimal, but I could examine them in decimal right here. And you'll see this first value is the decimal number 1001. So that is the number to be printed at that location, which was pushed onto the stack. The next thing that was pushed onto the stack, this was the number to be printed. The next thing was whatever's in EDX. So let's look at what data is at EDX. All right, here's a bunch of hexadecimal data, and that is in fact printable characters. And we can see the strings by doing 1S to see it as a string, and you'll see that is the format string. So when you enter the printf command, it looks on the stack, and it expects to find the value to print and the format string on the stack. So if you were to just call the printf and not push data on the stack, it will just take whatever it finds on the stack and interpret it as the data it needs. This is the fundamental problem, which we're exploiting all the way through here, is that C has like amnesia. It's incredibly stupid. It processes one command at a time. So when it goes down here to call a function, it just assumes that you must have previously pushed the necessary values onto the stack. But when it goes here, it does not know that you have failed to do that. It doesn't ever argue with you. It's very much like the buffer overflow. So let me go back to my slides where I talk about this a bit. All right. So that puts 2 arguments on the stack and calls printf. So it finds 2 values on the stack, the number to print and the format string. And if you print the format string alone, it will just print whatever it finds on the stack, even though the developer did not put it there. So if I get out of this and I cat format2.c again, and then I run format2, it prints 1001, and then it prints various random numbers. It just prints whatever was on the stack. Now, I got the format string, but I did not push any values to print, so it just prints values on the stack. So this is an information disclosure vulnerability. It's printing data which the developer did not in fact place there intending for me to print it. So I'm seeing some kind of internal numbers from the program that I was not supposed to see. All right. So here's the format strings we're going to care about here. %x prints a number in hexadecimal. %8x makes it 8 digits long by padding it as necessary with zeros. And you can make that as long as you want. 100x will be 100 characters long, padded with spaces or zeros or something, but the end result will be that long. So format string vulnerabilities exploit the stupidity of C. If I make a variable that has room for 10 characters and just put in more than 10 characters, C just does it, because when it goes down to the string copy command, it has forgotten the command that came before. It doesn't remember how big this should be. It just trusts you. Well, start here and put in that many characters. It is the programmer's responsibility to realize that it will put too much data in there, and you have to keep track of that. That's the reason why we have all these flaws in C. It puts a lot of burden on the programmer. So if I print without arguments, this ought to just give an error message. I cannot think of any reason why you would really want to do this, but C just does it and prints them out. So that's an information disclosure vulnerability. But it can be used to take over the box. So let me open this one up, which is ED204. All right. So this is the one I use in my projects, instead of that one that you mentioned, that old WS thing that's out of date and not interesting. Point C. All right. So I just wanted to cat it, actually. Okay. All right. So what this one does is it takes the first argument from the user, copies it into a buffer, and then prints it. So it takes whatever you give it and prints it alone here. So if you were to give it a string, it would print the string, but if you give it a format string, it will print it interpreting as a format string. So if I run this one, which is ed, all right, there, and I give it hello, it will print hello. But if I give it a format string like %x, then it prints %x, which prints some value from the stack. So I can put in a few of these, and I can put something in between them like a dot to tell them apart. And here I'm getting a variety of values from the stack in hexadecimal. All right, now let's talk about another crazy thing, %n. Notice now I get a segmentation fault. Now the %n format is a bizarre format string present in C. I have no idea why it exists. Instead of reading a value from memory, it writes to memory, which is just what you need to take over the machine, and I cannot imagine any reason for anybody to actually want this crazy thing. It's going to write to a location in memory, and the location is going to be the address it finds at this point on the stack, and the number it writes is going to be the number of characters that have been printed so far. So apparently, the point of this was to help format the length of some thing you're going to print or something like that. But anyway, the point is, by carefully using it, we can write to memory locations, and we can control the value we write there. So that's the game. And therefore, what we just did is elevating our information disclosure to a denial of service, or changing it to a denial of service. Now we made the program crash. And to get code execution, we just need to find a RAM location to write to, which will gain us control of the machine. And by the way, this flaw applies to a whole series of printf-related functions in C. Yeah, it's very strange. And by the way, these vulnerabilities are extremely easy to catch by looking at the source code for something that is printed without having two arguments. You should have one argument for the format string and one or more arguments for things to print. It's, anyway, that's the way it is. So it's easy enough to print these. But let's consider what other defenses will do. A stack defense will not stop this. Things like a canary value, address space layout randomization, non-executable stack, none of these are going to stop a format string from running. Static code analysis tools could easily do it just by looking at the source code. GCC doesn't seem to have any format string defenses. It didn't even pop up any warnings when I compiled this obviously flawed code that printed out a format string with no variable. So, the exploitation technique. First, you find a write operation you can control. Then you find a target RAM location that will control the execution. Then you write to that location, insert shellcode, and write that shellcode address to the target RAM location. Any recommendations on a static analysis tools? Well, Flaw Finder is the one I found best of like the easy, small, free ones. There are a lot of complicated, expensive ones, but I think Flaw Finder actually finds this, and other ones did not. But I might be remembering it that wrong. I remember I tried a few of the easy ones like Lint and such, and Flaw Finder seemed to be the most effective. There is a lecture in it towards the end of this course. If you go to the lecture notes or a previous time I taught it, you'll see. Towards the end, we try a few of these tools. They're all remarkably ineffective at catching these exploits, though. So, to control a parameter. So here's something. If we use this program now, we can print things out. So let's try this. If I run ed204, and I put in, let me see my chick, it's AAA, okay. If I put in 4 A's, the thing we usually do because it's easy to spot in hexadecimal, and then a few %x's with dots between them just to make it easy to read. All right, so notice, here's the 4 A's I put in, then here's the first word, second word, third word. The fourth word contains the A's I put in. So if we put text 4 bytes here, those 4 bytes appear as the fourth parameter on the stack. So now we can control the value here by putting it here as 4 bytes. But those bytes may not be printable, which is why I had to go back down to Python 2 to print that kind of stuff. Although some student says they actually figured out how to do it in Python 3, and I was only able to get halfway through that before I ran out of time preparing today's lecture. Anyway, And in your textbook, it's like 300 parameters down the list in that WSFTP thing, so it's much more complicated. But in this simple program, whatever you put there just appears as the fourth byte, so it's much easier. The exploits are much smaller. And by the way, you can check it. If you don't believe the AAA, you can use 1, 2, 3, 4 instead. And this is 1, 2, 3, 4. Remember, 31 is 1, 32 is 2, and the letters are in reverse order, as we talked about before, because it's little endian. So you have to put the bytes in reverse order. So now we can control this value, which means we can control the address we write to. Now we need to pick an address to write to that will control parameters. Now you could find at the end of a stack frame the saved return address and write there, and that would be okay, but that value depends on the size of the stack frame and such, and it's sort of hard to find. What's easier is to use the global offset table. That's what we're going to do, which is the table of pointers to C functions. Another thing you could do is find the destructors table that's called when a program exits, or other C library hooks. But we're going to go for the global offset table, which is an easy one. Here's some other objects in principle. And on Windows, you can do the unhandled exception handler, which we're going to exploit the exception handler later in the Windows section. But the easiest thing to do is just find a function, a C function, to exploit. So if we do GDB minus Q, this E function, ED204, and disassemble main. All right. So here it goes. It calls some thunk thing, which is part of setting up the stack frame. Then it calls printf. Then it calls exit. So what we could do, this printf is where we have the opportunity to exploit it. This printf thing is the thing with the print format vulnerability. So it's later going to call exit. So if we overwrite the pointer to exit, we can take over the execution. So that's our target. Let's get out of here. And, all right. So we can find those with objdump minus R. We've used objdump before. Objdump minus D shows you the decompiled, disassembled code, but objdump minus R shows you the relocation records for a program. And here they are. These are the addresses with pointers going to the functions used. And see, not very many functions are used in this simple program, just printf, string copy, and exit. So we can override this address, 0804A014. And then that address will be used to try to find the exit routine. So that's our target. All right. So we can write to it by putting in that data here. So let me go to my project instructions, which have stuff I can copy to make this easier. This is the format string project ED204. All right. And I've left the old Python 2 instructions here because I got fed up with doing it the hard way. This is the part I want. All right. So to do it live, it's here. Okay. So we will debug the program again. Okay, and now we're going to examine that location that points to exit with x/1x 0804A014. And you see it's exit at global offset table dot procedure linkage table, I think is what they call it. Exit is here, 0804, that's where it goes to. Now I'm going to run the program with a format string parameter that will overwrite that variable. So what this is going to do is feed in that address backwards, 14A00408. Those are the 4 bytes. And then %x, %x, %x to get to the fourth parameter. And then %n is going to write to the address in the fourth parameter. And this is the address in the fourth parameter. So it should write something into that location. So we run that. We get a segmentation fault. It's hit an error message of some kind because we have corrupted the exit pointer. And when it tried to exit, it went somewhere stupid. And let's see where it went. If we examine that location, it now contains 000014 because remember, it writes a value there, a 32-bit value, which is equal to the number of characters printed so far. And this is the total number of characters, which I guess is 14. So that's why it was important to have format strings that will control the length of what you're printing. It is the number of characters you print that determines what value you write there. So now we have the ability to create another denial of service attack. We can now modify a pointer which causes execution to redirect to a stupid value, which causes it to crash. So all we have to do is refine it a little more to control that value. All right. And so here's the code to write 1 byte. And now we got to make the code that writes 4 bytes. And there it is. And let me get it from my example here, f2.py. All right. And because I'm using Debian 11, it's a little bit different than what I wrote in my instructions, but not much. So if I let's see if I have f2.py. Yeah. Right? Yeah, that looks right. So I was trying to hit a controlled value, AA, BB, CC, DD. So I'm trying to write now, let me see, let me try my other one. I think I'll start with F1. There we go. All right, so here I'm going to write 4 bytes. Remember so I'm going to write first to that address ending in 14, then in 15, 16, and 17. So I'm going to write each byte one after another. So I print this group of 4 bytes, that group of 4 bytes, that group of 4 bytes, that group of 4 bytes, and then the format string, which is skip the first 3 words. The 4th word you write. Then there's another one that's just a hexadecimal word. That's this junk that you're not using. And then the %n again to write, and %x, %n, %x, %n. So these 4 strings will now write to these 4 values. So I will write to the 4 bytes in the 32-bit word 1 byte at a time. That's what this one will do, f1.py. Now, if I want to test it, I can run f1.py. And it prints out stuff, but it's not obvious that it worked because there are a bunch of non-printable characters in there. So if I want to actually make sure it works, I can write to foo, and then I can use xxd to look at foo. And now I will see it does have these values 14, A0, 0408, and then junk. And then again, so you can see it is writing the 32-bit word I want, and then just junk, and then the next 32-bit word I want, and then junk, and so on. This is a good way to check the output of a thing like this, which is writing non-printable raw hex bytes into a string variable, which is what you have to do for this kind of exploit. So let's debug that program again. There we go. And run the program with the output of f1.py used as the argument, which is going to be this string. Again, it's going to hit a segmentation fault. And now we can look to see what value it wrote in the pointer that goes to exit. So this ought to be going to exit, but now it's going to 30, 38, 40, 48. Because after each one, it then prints 8 more characters before it goes to the next one. Yeah, you can pipe it in XSD. That's right. Yeah, I know you can. But I like doing it this way. All right. So anyway, that's the... All right. So now we've been able to write 30, 38, 40, and 48. So we just have to make a program that will compensate. And what we're going to do is control the lower byte. So in order to get an arbitrary value, we're going to get this up above 256. So we can hit 0 on every possible byte here. And each one of them is going to get above 256. Yeah, that's right. Good. The random student's got a good point there. All right. So here's where I'm going to need to modify my code a little bit. So the lowest value is 30. So if I look at my f2.py, I could try subtracting 30 from each of these. And I'm going to target AA, BB, CC, DD. Now it's going to turn out this isn't exactly right, but it's a start. So let's try that. And so I make the first number 256 plus B1 minus 30 to try to get this value in there. And 256 times 2 times 3 times 4, because I have to make the total length of the thing grow and grow. And so the point of this is after each one of these times, the total number of bytes printed so far would be related to B1 in a way to hopefully put that there. So this is my first attempt to do it, and I think I'm going to be off by a little, but it's not terrible. So that's F2. So if we debug it again, and then we run the code with F2, now we examine the value. All right, now I wanted AA, BB, CC, DD, but you see I'm 7 short here and 7 short there, so I'm 7 short everywhere. So I need to print 7 more characters for each one of these. So let's get out of here. And edit my code. I just need to add 7 to each of these. A lot of ways to do it. I'll just do it the simple way, plus 7. I think adding 7 to the first one is probably all I have to do. No, because it's going to change. All right. I think I have to add 7 to each of them. We're going to try it. This is where I'm not sure I'm exactly right. We're going to see. All right. Let's see what that does. Run this and run it with the F2. Ah, that looks good. AA, BB, CC, DD. Good. That ended in the instruction pointer, so I know it worked. And if I examine that value here, there it is. AA, BB, CC, DD. So now I have a program that can write any address I want there. All right. So now I've got that ability. This is what we want. All right. So now we can put in dummy shellcode. And it might be as far as we go tonight, but the dummy shellcode we're going to put in is a NOP sled. NOP times 90, and then some shellcode CC times 250. CC is a break. So 90 will execute but do nothing, and CC will break back into the debugger. So this is the size of real shellcode to make sure I have enough room, and it's just going to write that right on the stack after this form. So it'll be somewhere in the stack, and I'm going to hunt and find it. So that's going to be my f3.py. So let me just prepare my f3.py for my example here. All right. So nano, I get out of here. Nano f3.py. All right. And now I need to put in those plus 7s again. Which is the only difference between Debian 10 and Debian 11 that I've noticed so far. All right, so that should do it. That will put in AA, BB, CC, DD, and it will put the NOP sled and shellcode on the stack. So I debug it again, and I run it with f3.py. Okay. And, oh, I forgot. Oh, my thing did not run. F3.py. I forgot to make it executable. I have to chmod plus x f3.py. All right. Now I can run F3, F3. Okay, good. And it prints. So, debug the thing. Run it with f3.py. Whoa. Control C. Okay, there we go. Now I get the seg fault, which is what I want to see, and then I get the AABBCCDD, so that's good. Now I want to examine that value, which should be AABBCCDD, and it is. And now I want to find my shellcode on the stack. This is a process we're going to do very many times. We gain control of an address, which controls the instruction pointer. We have managed to inject some shellcode somewhere, but we have to find where it is. So we have to look on the stack. So I'm just going to do x/200x. Whoa, not listening to me. x/200x ESP. There. And see, here it is. Here's the 90s. That's my NOP sled, and here's my breaks. So that stuff there is my shellcode. So now I can choose what value to write. and I can just choose any value I want in this region. The only thing I can't do is choose a value that includes a null byte. But this looks like a fine address, FFFFD04C. Let me see what I used before. Before I used D, it was a little different my last. So I'm going to use this one, FFFFD04C. So let me copy that and put it in a text editor so I don't forget it. All right. So let's put that in my extac. So Control C, Q, yes. All right. Let's copy F3 to F4. All right. So those are the bytes I want to put here. So I'm just going to put it in here as a comment. There, that's the address NOP sled. That's where it is. So I want 4C, D0, FF, FF. There we go. So let's, it should be executable. Let's check it. F4.py. All right. It's executable. Oh, /. All right, there we go. So let's gdb -q ed 204. Tab completion doesn't work for some reason there. All right. And now I want to run f4.py. And notice it didn't crash, it hit the breakpoint here. So that's pretty cool. And I can probably put a breakpoint in the machine to test it, but I don't know if I really need to. It made it through to the breakpoint at this location. Let's take a look at that and see if I do X, 200X, ESP. I may not be able to do it anymore. Okay. And there's the 90s, and there's the Cs. So if it slid down the NOP sled, it would hit a C here at FFFFD0. This is HC. This is 94. D094 is where I'd expect it to stop. And there it is, D095. So it executed the CC at D094, and the next instruction pointer was D095, and then it stopped because it was a break. So we did succeed in reaching the shellcode and running it. This is a real important test, because one common problem is you have data execution prevention, and even though you can inject code, you can't run it. But on this machine, I can. All right, so let's go back to my slides. We've inserted the dummy shellcode, we found it on the stack, and we ran it, and it hit the trace breakpoint trap, which is what it would do, indicating that it did slide down the NOP sled and hit the CC. All right, now, you can test the thing to see what characters can't be added, and it turns out tab, line feed, carriage return, and space are things that tend to break strings. So I was able to make a test. I don't think I'll bother doing it live, but you just print all the bytes in order. So I have 01, 02, 03, 04, 05, and so on. And you can see some of them didn't get there. You have to skip certain characters. So you find out what characters are allowed, and now you can generate real shellcode with MSF Venom, which is part of Metasploit. And so we're going to make 32-bit Linux shellcode, and we're going to dodge these bad characters, null, 9, A, D, and 20, which is null. I think 9 is tab. This is line feed and carriage return, or carriage return and line feed, and that's space. And it turned out I had to turn on this option prepend fork equals true to make it work. There are a few advanced options when making shellcode, and it seems to work better that way. And then you tell it to create the shellcode in Python, and you just have Python 2 code to put in. Well, I think it also works in Python 3. So let me do that live here. Going down to my, there we are. There's the command I need. So let me go to my here. All right, get out of this, get out of this. All right, so let's copy F4 to F5. All right, and now let's generate the shellcode, which is going to be this. And I might need a sudo. Let's see if that works. I do not want to do whatever you're talking about. Okay. Maybe I'm going to have to run it twice. Maybe it's still working. Let's see. Ah, okay. Just had to wait a little the first time I ran it. So here is my shellcode, 664 bytes. But that's the Python file, which is just because it's expressing things with this long phrase, \xdb for 1 byte. The actual payload is only 133 bytes. So it will fit in the payload region that I've set aside for it. So I copy this, and now I nano my F5, and I insert that code someplace, like here. There. And now, I just put it in instead of my shellcode. And there. Now what I'm going to do, it's probably not important for this exploit, but it's a very good practice to always keep the total length of your exploit the same. So what I'm going to do is I'm going to not use this shellcode, but I'm going to use this buff, and I'm going to make sure the total length is staying 250. So I'm going to set my shellcode equal to buff plus any kind of padding, which is going to be A times 250 minus the length of the shellcode, length of buff. There, that should do it. Now this shellcode is the same length as that shellcode, and when it prints it, it'll just put it in the same place. So that should run this. That's my egg. And I left in 100 bytes of not sled, which is a really good idea. I think I mentioned this before, but I'll mention it again. Don't ever use Metasploit payloads without at least 16 bytes of not sled. A lot of them will not work. A lot of them use the first 16 bytes of this not sled as like a scratch pad or something. And if you cram it into a space too tightly, it will fail. So this should work, F5. And what it should do, by the way, it should do a shell bind, which will start listening on port 4444 by default. So let's debug that program. And run it with F5. All right. And I hit a segmentation fault with a funny value there, so I wonder what I did wrong. Oh, I don't know. See if we figure out what I did wrong here. Any of you smart people watching might have caught it. Well, we can do it by putting in a break. Let's disassemble main. And I thought it was around 115 we want it to be. Well, here's the printf. And there's the exit. So if I want to examine what I've done, I just want to break after the printf. So let's well, I might quit now. I've fallen off the track. It should have been main plus 115. I think I'm somehow debugging the wrong executable. Let's get out of here and see what I'm doing. All right, get out of here. I say quit. Yes. ED204. No, ED204 is the right executable. Okay, what have I done wrong? Let me just try running the F4 again. Let me disassemble main and see if I can figure out why I thought I needed to be down at 115. Down here, okay. There's a printf up here, but that's not the one that matters. The one that matters is the one down here. Okay, now I'm understanding what happened. So here is the printf. Okay, so let's break there. This is after the exploit. So break star main plus 115. All right. Now we're going to be able to debug our exploit, I think. Okay, we're running it with F5, and now it's stopped. So now we should be able to examine the value in the pointer that goes to exit, which is here. Okay, and that is FFFFD04C. So let's see if that's right. If I examine the stack, D04C is later. I guess I need to look at 200 bytes on the stack. Still off the end. So my exploit doesn't seem to be anywhere near where it should be. Let's try more, but I think something has gone badly off track here. I don't see the injected code at all. Oh, there it is, way down here. Oh, D04C. Okay, it's further down the stack than I expected it to be, but D04C should hit the NOP sled. All right. And it should continue down here. Here's the NOP sled, and here's the egg, and here's the 41 padding I put in. So really, it should work. All right. If I continue, it terminates and no longer exists with it. But the segmentation fault bothers me. I don't think that's right. But let me... if I quit and then do a sudo ss -pant, yeah, it's not listening. All right, so this didn't work to some extent. I'll probably fix it again. Do I need a U limit for the process? No, I don't think I do. All right, folks. Well, like I thought, I'll have to revisit this next time and explain what went wrong. Something fell off the track towards the end there, and I can't fix it right away. But this tends to happen. So I'm going to stop this video, and we'll take a break, and then I'll try demonstrating the simple buffer overflow, which will hopefully work better.